Hi everybody, Physics Ninja here. Today what I want to do is look at 3 body mechanics problems. Alright, the first one is a bicep curl. So we're going to look at the forces involved when you lift something with your hand, okay? And we have a tension force in the muscle, a reaction force at the joint. See how you solve a problem dealing with bicep curl. The second problem I want to look at is a problem where you're lifting up a heavy object and using your back to lift it. So how can you set up a simple equilibrium problem? Look at the torque involved and the tension in the back muscle, for example. And in the last problem, I want to look at a foot problem where you're standing on your toes at a certain angle and you want to calculate the reaction force, the force of the tibia on the foot, and maybe also the force of the Achilles tendon pulling upward. Okay, so like with all my problems, if you like it, give it a thumbs up. Consider subscribing to my channel. Okay, let's get started. All right, here's the arm curl problem. A person holds a 65 Newton weight in his hand. The bicep is attached over here 2.5 centimeters away from the joint, which is depicted here by the letter O. And the weight is 36 centimeters from that joint. Okay, that's kind of from that position. Find the bicep force on the forearm and the force acting at the joint. All right, so we kind of have two things we want to look at. The weight of the forearm is 30 newtons. All right, with all of these problems, it's always good to draw a free body diagram, and that is simply a simplified picture of what is going on. So I'm going to represent the forearm here by this bar, and here's the O point. Now, we have to consider the different forces. One is the bicep force. So I'm going to consider that force. We're going to call that a tension T. What else? So we should have the weight, right? The weight maybe of the forearm. Let's maybe put that one acting straight down. Call that maybe just Fg for the force of gravity acting down. We also have this, kind of bowling ball looking thing at the end of the hand. So we also have to add the weight of this object. I'll just call it W and maybe ball for this one. All right, now we should have another force, right? There is where the bones connect here. We should probably have another force. We're going to call that one a reaction force, and I don't know which direction to put it, but let's just assume that it's going to be down, and I'm going to call this one R. Now, you could have put it up, but that's okay. The physics is going to tell us whether we're right or wrong. So at the end, what we have to do now is apply Newton's laws, and in order to do that, we have to choose coordinate systems. Okay, so what I'm going to do here for forces, I am going to call the up direction to be the positive direction. And we're also going to have to write torque equations, okay? And what I'm going to do here is I'm going to define that forces that tend to make this forearm rotate counterclockwise, we're going to call those positive torques. And forces that tend to make the object rotate clockwise, we're going to call those negative torques. Okay, so now what we have to do is basically add the forces in the y direction. Okay, so what are all the forces? Well, we have 4 forces, so we should have 4 terms over here. Let's start maybe with the tension. The tension is acting up. Call it positive T. Now what else? We have 3 forces acting down here on my diagram, so I should have negative R for that reaction force. Negative, the force of gravity acting on the forearm, and negative, the weight of the ball. Again, if I add all of those up, those should equal to 0. All right, so this is kind of one important equation. Our next equation now is going to be adding all the torque. Now, in order to define the torque, you have to place a pivot somewhere, and you can place the pivot anywhere. It's completely arbitrary. Some cases are better than others. In this case, if I place the pivot right here at this point denoted by O, the advantage of picking a pivot at one specific position is that you never have to worry about the torque produced by that force because it's acting right at the pivot and therefore produces no torque. So then we're simply left with the torque due to the 3 remaining forces. So that's what we're going to do now. So we're going to have the torque due to the tension force. Now let's maybe add some of the distances here since we need those for torque. So this distance is the distance from the bicep to the joint. So that's 2.5 centimeters. I'm just going to right away write it in meters. All right, there's one more distance we have to worry about. That's the total length, right? And that goes from the joint all the way to where the ball is, and that's 36 centimeters. Okay, so now we can go ahead and calculate all these torque values. So the torque due to the tension, first of all, if the tension is the only force acting on it, it would tend to make it rotate counterclockwise. So this is going to be positive. And the torque is simply T multiplied by that distance. In this case, it's 0.025. All right, we're left now with two more. Both of these are going to be negative because both of these forces would tend to make this object rotate clockwise. So if I consider first the force of gravity, it's Fg. Now the distance to the pivot for this one is going to be 0.36, but it's half of that, right? Because it's acting kind of at the midpoint of the forearm. And the last one we have to consider is the weight of the ball. The magnitude of the force is W ball. And the distance to the pivot here is actually the full 36 centimeters. All right, and that should be equal to 0. Now let's look at both of our equations. So we have equation 1. Our second one here is our torque equation, equation 2. What we want to do now is we want to calculate this tension force, and we also want to calculate this reaction force. If we start with equation 2, tension is actually the only unknown in equation 2. So what we have to do is just a little bit of algebra in order to solve for that. So we have T multiplied by 0.025. I'm going to bring the other two terms on the other side, and that'll switch those signs. So we're going to have the force of gravity. And again, this term here is going to simplify to 0.18, and then plus the weight of the ball multiplied by 0.36. All right, we can now just get one final expression for the tension, and let's right away substitute in what the force of gravity is for the forearm and also the force of gravity for the ball. We know that the person holds 65 newtons, so that's the weight of the ball, and we have 30 newtons for this force here. So this term looks like this, plus 65 is the weight of the ball multiplied by that distance. And again, at the end, I can't forget I have to divide through by this distance from the joint all the way to the bicep muscle. All right, if we substitute in all our values in there, we should put that in the calculator. At the end of the day, I think I get 1152 newtons for that force. Let's go ahead and highlight that. Okay, so that is my tension force. Once you have the tension force, you can go now to equation 1. Equation 1, we also wanted to find what is this reacting force, R. That's the only other unknown in this problem. So let's go ahead and write an equation for R. I'm going to bring it on the other side just to swap the sign. And what you end up getting here is R equals to T and minus the weight of the forearm and minus the weight of the ball. Okay, so just substitute 1152 minus, this is the forearm, that was 30, and the weight of the ball was 65. Put that in the calculator, you should get 1,057 newtons for this reaction force. Let's go ahead and highlight that. Okay, kind of a pretty nice, straightforward body mechanics problem involving the bicep. Here's our second problem, lifting a box. So we have this person here who wants to lift a 200 Newton box by bending forward. His body here weighs 350 newtons, and we assume that it pivots here about the base of his spine. The angle between the spine and the back muscle is 10 degrees. What we want to do here is find the tension in that back muscle and the compressive force in the spine. We have a simple kind of vector diagram that depicts some of the forces involved in this problem. We also tell you that the back muscle is attached at a point that is 2/3 up the length of the spine. So here's a free body diagram on the spine. Let's look at all these forces. So we're going to have this tension force, which represents just the weight of this box that I'm trying to lift. We have the tension force, which is the back muscle, which is what we're trying to calculate here. Now that distance between the back muscle and, say, the end over here is 2/3 of the total length. So this here would be 2/3 multiplied by L, and the total length is L. So what else? We also given that this tension here makes an angle of 10 degrees, say with respect to the back. We have the actual weight of the back itself, right, or the body. It's 350 newtons, so this guy we know. And then we have the reaction force at the spine, okay, at the base of the spine. We have Rx, and Rx is a compressive force. You can see it's kind of acting to try to compress the spine. Okay, so that also is something we're trying to calculate here. What is that compressive force, and what is the tension? So there's really two things we want. We're going to proceed using the same approach as the previous one. We're going to use the same standard coordinate system for the forces. call this positive X, call this positive Y. And again, for our torque, counterclockwise is positive, clockwise is negative. All right, once we have that set up, now we're going to set up the sum of the forces. Let's do it in each direction. Again, it's an equilibrium problem, so both of these should sum to 0. All right, so what do we have in the x direction? Well, there's only two forces in the x direction. We have this compressive force that we're trying to solve for, and then we have a component of the tension. So this guy looks like T and cosine of 10 degrees if you do that carefully. What else? Now in the vertical direction, we have three forces. We've got Ry acting up, and we've got basically two forces acting down. We have the force of gravity acting on the body, and we also have this weight of the box, which I'll just call, say, minus 200. All right, so that's good. And then our last equation is the sum of the torque. Well, if you're going to calculate torque, you need to place a pivot somewhere. Again, it's completely arbitrary. I'm going to place it here at the end. And the nice thing about that is it cancels out any torque due to both of these force components, because those force components are acting right at the pivot. All right, so if we add up all the torque, we want that to sum to 0. So now we have to consider all of the three remaining forces. So the torque due to the tension, well, in this case, it's going to be the magnitude of the force. The distance to the pivot now is 2/3 multiplied by the length. And we also must include this sine of 10 degrees for this case. If this force is the only force acting on it, it would tend to make the back rotate counterclockwise. That's a positive torque. We should then have two negative torques. We have the force of gravity. I'll just call it Fg. It's acting a distance equal to half the length. Let's just place it in the middle. And then we have the force of the box, or the weight of the box, which is going to be 200. And that is acting a distance L away. All right, so again, now we have three equations. Let's look at them. I usually like to start with the torque equation. If I look at the torque equation, actually the only unknown in the torque equation is the tension. One other thing I notice in the torque equation is that we're not giving you the length of the body. However, you see the length is in all three terms, and therefore you can divide through and basically cancel out that term. All right, so let's go ahead and rearrange. The only thing I want now is the tension. I can bring both of those terms on the other side, and I should get something like this. So I'm going to substitute the value of the force of gravity of the body. So that's 350 over 2 plus 200. And then I have to divide through by a whole series of terms, right? I have the 2/3 sine of 10 degrees. Okay, if I go ahead and put that one in the calculator, at the end of the day, I think I get 3,239 newtons. Okay, so that's the tension force. Let's go ahead and highlight that. All right, and the last part was, what is that compression force? The compression force is Rx. Well, let's look for an equation now with Rx. That's pretty straightforward, right? It's the first equation we wrote. I could right away write as Rx is T cosine of 10 degrees. And now we could just solve for the value of the tension force. We can go ahead and just substitute that in. Cosine of 10 degrees. Therefore, Rx, put that one in the calculator, you get approximately 3190 newtons. All right, highlight that term. So there's kind of a nice problem involving some angles, all right, including the angular term for the torque and reaction forces from the back. All right, let's go to our last problem now. All right, last problem here, we're going to consider what happens when we're standing on our toes. And the problem is when a person stands on their toes, the weight of the person is supported by the normal force. A simple model for the foot in this position here is shown over here by this free body diagram with some of the forces. So where T is the tension in the Achilles tendon, R is a reaction force of the tibia pushing down on the foot. Okay, we've given you some of these angles for this problem, so we don't have to worry about that. At the end, we want you to find values of T and R so that this foot is in equilibrium. The weight of the person is 750 newtons. So let's go back to that first sentence. They say that the weight of the person is supported by the normal force. Okay, what that statement means is they basically just want you to set the normal force equal to the weight of the person. It's not super clear what that means, but for this problem, let's just set it to here. And the rest of the problem, all we want to do is determine these forces. Same type of thing as what we did previously. Same type of coordinate system, positive x, positive y. What else? Torque, positive torques counterclockwise, negative torques clockwise. And now we just turn the machine, right? We add the forces, say in the vertical direction. Let's see what we have in the vertical direction. Well, we have plus n acting up. What else? We're going to have a component of this reaction force. That's pointing down. And if you do the trigonometry correctly, you should have r cosine of 12 degrees in this case. What else? We have a component of this tension force. The tension force is at right angles to the foot for this particular foot. And again, we're just looking for that vertical component. So again, it should be t cosine of 20 degrees in this case. The angle's a little bit different. All right, so that's it. That should be equal to 0. If I was going to sum the forces in the x direction, there's no x direction for the normal force. We do have x directions for the reaction and the tension force. So that means that this guy here should be r sine of 12 degrees and minus t. Again, we're looking for the x component, so that should also be sine of 20 degrees. Add those, and that should also be equal to 0. And now the last the last equation rather, is you must sum all of the torque. So the question is, where are you going to place the pivot in this problem? Again, you can place it anywhere you want. Here, we've always been placing it at the end. Let's place it here. Right? And if I place it here, in this case, let me just go ahead and write pivot. That means you never have to worry about the torque due to this reaction force if I place it here. The only thing that's left is the tension and this normal force. So that should be pretty straightforward. So let's start with the tension. The tension's pretty easy because it's at right angle to the foot. So if you want to just add the torque due to the tension, in this case it would be T. Now what is the distance now from the pivot to where the force is being applied? In this case it should be this 25 centimeters, the whole length of the foot, minus this distance, right? So you're left with, that looks like 7 centimeters. Right? So I write something like that. Now what we have to consider is the normal force. Now the normal force is at kind of a strange angle relative to this foot. So there's many ways of doing this. I'm going to do it this way. I'm going to break the normal force into two components. There's this component, that's the normal perpendicular to the foot. Because at this angle here, you should be able to convince yourself that this angle here is also 20 degrees. And there's a component of that normal force that is parallel to the foot. I'll call that n parallel. Now, if you look at the n perpendicular, this should be the normal force multiplied by cosine of 20 degrees. And this guy here would be the normal force sine of 20 degrees. Now, there's only one of these components that produce torque, right? And that would be the perpendicular component to the lever arm. Okay, so that's what I'm going to use for my force. So we're going to have, first of all, it's going to be negative because this component of the force would tend to make the foot rotate clockwise. So we're going to have the magnitude of the force is n cosine of 20, right? This is all we're worried about. The distance to the pivot now is the full 18 centimeters, so 0.18, and then that's it, equals to 0. You would have sine of 90 degrees in our definition. All right, so let's go back to our questions. We have the three equations, we have all the physics here. Now we just have to do the math and solve. We want to solve for the tension. Again, I like kind of equation 3. It's the only unknown over here in our equation. So let's go ahead and do this. So we have tension must be equal to, I'll bring this whole term on the other side, and you can substitute our n value for the 750 newtons. So we get 750 multiplied by cosine of 20 degrees, and all this multiplied by 18 centimeters, divided by 7 centimeters. All right, we put that in the calculator. We should get that the tension force equals to roughly 1812 newtons. Let's highlight that. All right, and our last question was, what is this reaction force R for this problem? Well, now you have a choice, right? We can either use equation 1. That looks a little bit more complicated. Equation 2 is probably a little bit easier. At least algebraically, it looks a little simpler. You can write an expression for R. You bring the t sine 20 degrees on the other side. Oh, can't forget my t. And now divided by sine of 12 degrees. All right, we put our value of the tension right here. That's 1812. Sine of 20 over sine of 12. All right, put that in the calculator and we get a force equal to 2,981 newtons. Okay, so that's the value of this reaction force. All right, folks, anyway, that's kind of 3 biomechanics problems. Hopefully they give you a little bit of insight on other problems that you might come across. Thanks for watching.